Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 5B of rectifiers, right? So we have studied about half-wave rectifiers and also half-wave rectifiers with freewheeling diode. We have studied about RL loads, RLE loads, E loads, RE loads, all those things. So in this lecture we'll mainly solve questions related to half-wave rectifiers with freewheeling diode and RLE loads, okay? And also we'll take more questions which is like the concepts that we learned in the previous lecture. So let's start with the questions. I gave you all these questions in the homework, right? So we'll do all these questions. The block diagram of an, this should be of the block diagram of an AC to DC 1 pulse converter. So this is basically half wave. This 1 pulse converter means it is talking about a half wave rectifier, right? Half wave rectifier, okay? Half wave controlled rectifier is shown in the below. The average output voltage is 0, okay? The average output voltage is 0. Then discuss about the following parameters. The load is R, RL, RLE, LE, L, RE. So can the average output voltage be 0 if the load is purely resistive? Is it possible? No, right? If it is EL, right, then also it is not possible, because there will be at least whenever the load current is 0, it will be only like battery will be present, and that voltage is E voltage, that will be always present. So it cannot be 0, it cannot go to negative, okay? So for RL, it can never go to negative, right? Because like there will be some positive portion. But if there is a pure inductive load, we have analyzed for pure inductive loads, we know, right, the amount of charging and the discharging is same, because there is no resistance. That's why the inductor energizes and de-energizes at the same rate, okay? Hence the amount by which it will charge, the SCR will be on for that amount of time, and the SCR will be on after pi for that same amount of time for which it charged, right? So these two amounts will be same, and overall the area will be 0. So if only L load is present, right, the average voltage across the inductor is 0, that we know with the voltage second criteria, and the average voltage across the inductor is basically the output voltage for a single inductive load. So L, like this will be single only. So I can safely say that the load is inductive, okay? Okay, next, what is the case? Next, the load current is constant, continuous, discontinuous. So here, right, load current will be continuous. Why load current will be continuous? Because or you can say on the edge of continuity, okay, on the boundary of continuous and discontinuous. Because for an inductive load, what will happen is that, okay, we cannot surely say about this. We cannot surely say, because if the SCR is triggered at alpha, right, then also we cannot say, okay? So here, right, okay, alpha is 60 here. Alpha is 60. So load current, right, will not be continuous, it will be discontinuous. Why it will be discontinuous? Why it will be discontinuous? Because discontinuous, because my waveform, right, output voltage waveform will be like what? Output voltage waveform will be something like this, that this is my VO, this is my omega t. So it will be 0 for this period, and at alpha, omega t equals to alpha, the device will be triggered. So the inductor voltage will change suddenly, and the output voltage will follow the input, and it will follow the sinusoid waveform, and it will follow the input up until what? It will follow the input up until pi minus alpha, right? Pi minus alpha. Pi minus alpha, okay? So it will be pi minus alpha. Now what can I say? Now basically, right, this point and after this, right, this, okay, this is not pi, this is 2 pi minus alpha. Like, I hope you're understanding. If you're not, you have to go and back and watch again the inductive load case analysis. So this will be up until 2 pi, okay? So here, whatever amount it got charged, this will de-energize here, and after this, right, what is happening? My voltage is 0, okay? And what happened here directly? What happened suddenly here? The inductor, the current, right? Current got 0. That's why the SCR got naturally commutated after this. SCR got naturally commutated. SCR is naturally commutated. What does natural commutation means? Natural commutation means the SCR turned off. SCR turned off. So if SCR is turning off, obviously the current is 0. So that means it is not continuous conduction, it is discontinuous conduction. So I should write here conduction, right? Conduction. Now next, freewheeling diode present absent. So here, right, if I talk about the freewheeling diode, in case of freewheeling diode, right, the average voltage can never be 0. Okay, average voltage can never be 0. Why? Because if there is R load, like there will be some positive part, right? There will never be a negative part. Then the average can never be 0. Average can never be 0. Only if the SCR is never triggered. If the SCR is never triggered, then obviously the average voltage can be 0. Okay, if alpha is greater than, then the alpha has to be greater than 180. Alpha has to be greater than this pi, right? Then only the SCR will never be triggered because it will be in reverse blocking mode. But here they have given my alpha as 60. As they have given my alpha as 60, then definitely my SCR will never, my SCR will be triggered in this positive half cycle. And if it is triggered in this positive half cycle, and then also it is telling me that the average voltage is 0, then it is not possible. It has to get some negative area as well, right? And as soon as I get a negative area, as soon as I get some negative output voltage, that means what? Freewheeling diode is not present, because it is not possible to get a negative voltage with freewheeling diode. Okay, we will always get either 0 or positive voltage. So VO can never be 0. Sorry, VO can never be negative. Okay, so you have to take care of this. Now let's come to the next question. These were the 3 solutions to this question. So this should be ABC actually, not 1, 2, 3. The LC will be confused. I should write this. Okay, next, the block diagram of an AC to DC 1 pulse converter. Again, this is a half rectifier only with freewheeling diode. Now this has freewheeling diode. They have specifically said to us, is shown in the figure below. Calculate the power consumed by the load. If the load current is ripple free, maximum current through the freewheeling diode is 10 amperes. If the load current is ripple free, right? If the load current is ripple free, that means it has no ripples with it. That means it is constant. It has no ripples. It is constant. That means it is constant current, and the maximum current through the freewheeling diode is 10 amperes. And what we know that the maximum current is equals to the average current is equals to the RMS current if the value of the output current is constant. That means this will be 10 amperes, right? As they have mentioned, maximum current. So, and output waveform voltage is as shown. Okay, so the output voltage waveform is shown, and I have computed the maximum like the current is ripple free. So I have to compute the power consumed. What will the power consumed? So power consumed, right? Power consumed basically will be, in this case, right? In this case, power consumed will be what? If I have I don't know what load is this. They have mentioned what load is this. Okay, they haven't mentioned what load is this. Like in our case, right? What we can do is, here one thing I can say. What is P of T? P of T is 1 by 2 pi. Okay, 1 by 2 pi V of T into I of T dt, right? V of T into I of T, or I can say d omega t, not dt actually, sorry, d omega t. Okay, so here, because I am dividing with radians, right? That's why I am writing here this also in radians. So here, what is my I of T? I of T is constant. I of T is constant. So I can write my P of not P of T actually, power, total power consumed. Okay, total power consumed, that is PO. So what will be PO equals to? PO equals to basically, I can take this I outside, right? Because this is constant, this is value 10, right? So this will be 10 divided by 2 pi integration of Vt d omega t. Now what is this thing? What is this thing? This is simply V average, right? So I can directly write this as 10 times V average. Okay. And I can do this integration, right? I can do this integration. I have been given the voltage waveform. So this is output, right? VO and IO. VO and IO. Okay. So what I can do is I can basically do this integration. I can do this integration from theta to pi. Okay. So from theta, they have told us theta. Okay. Theta is not given. Okay. This should not be theta actually. This should be alpha. Sorry for that. This should be alpha. I've done a mistake over here. This is not theta actually. This should be alpha, right? Sorry. Or am I correct here? This should be alpha. This should be alpha, right? My bad. Because only after alpha it is the device will get triggered, right? So then only. So alpha is 60 they have given. So basically like we know what this formula is, right? What this is equals to what? 10 divided by 2 pi into Vm. Vm is there. What is Vm? Yeah, Vm we can find out from here, right? 230 into root 2. 230 into root 2 into 1 plus cos alpha. 1 plus cos alpha. What is cos alpha? Alpha is 60. Okay. So what can we write? What can we write? What can we write here? This is 230 into 2 into 10 divided by 2 divided by pi into cos 60 is half, so it will be 1.5, so it will be 776.52 watts. Okay, 776.52 watts. So my output power, right, power dissipated by the load will be 776.52 watts. Okay, so this will be the answer to this question. Now what else can I say? Like this is the answer. So let's go to the next question. Next question is, in the circuit shown in the figure, the value of inductance is very large. Okay, and if they have not given you the inductance value, right, so you will assume it is very large, and what you will assume is that then the load current becomes constant because it becomes ripple free. The average value of the load current is 100, and if the value of inductance is very large, right, it will take more time to discharge because I have a freewheeling diode here. So I will assume the average current equals to the RMS current equals to the load current, that is 100 amperes. So this is my constant current. Find the delay angle at which the thyristor is gated. Okay, so to find out the delay angle at which the thyristor is gated, if the average current they have given us 100 amperes, how do you find that? So we know what is the load, right? Load and E, all these value we know. So from there we can find out the VO average. And what is VO average? VO average is basically equals to IO average into R in plus E. Okay, so from there we can directly find out what will be the angle alpha, because VO average will come in terms of the varying angle of this thyristor. Then obviously we have to compute the power consumed by the load. That is very, very simple, that we can do. And load is this, right? Load is this whole thing, RLE. RLE is the load. So we can use this simple. So they have given me that IO average is constant. IO average is this. Okay, IO is a constant value, that is 100 amperes. Now what is my VO average? So my VO average is basically IO average into R. IO average into R plus E. So it is 100 times R. What is R? R is basically 0.01 ohms. 0.01 ohms plus E. E is what? E is basically 20 volts, right? 20. So this is 1 and 21. Okay, 21 volts is my average output voltage, and I know the formula, right? This formula you can remember obviously, but how much time will it take you to derive? 10 seconds, maximum 10 seconds. Okay, so I know the formula that VO average also is equals to Vm by 2 pi 1 plus cos alpha. Okay, so this will be equals to what? This will be equals to 21. So Vm, I know Vm is 200 root 2 divided by 2 pi, and okay, I will just cross multiply and okay, compute this real quick. So 21 into 2 into pi divided by 200 into 2, and okay, am I doing something wrong? 21 into 2 pi, okay, fine, divided by 200 root 2, fine. I have to subtract this by 1. Okay, I will subtract this by 1. So cos alpha will come out to be something negative. Cos alpha is equals to minus 0.5335. okay, and if I take the cos inverse of this alpha will come out to be 122.24 degrees. So alpha will be 122.24 degrees, and this will be my answer to the part A. This will be my answer to the part A. And whenever this current is constant, right? Whenever this current is constant, your power will become simply VO average into IO average. You can cross verify. I will show you, right? So because this is constant, right, I can take it outside the integration just as I did here, right? So that's why it becomes that. It is not always the case. Only when the power is constant, only then we can do this. So just be careful about this. So okay, so B is what? B is PO equals to IO RMS whole square into R plus E into IO average. So IO RMS is basically IO average only, which is what? IO RMS is 100. So it is 100 whole square into R. R is 0.01 plus E. E is 100. E is 100. No, E is 20 only. E is 20 only. Into IO average. IO average is what? IO average is 100. Okay. So what will be this? This will be 100 whole square into 0.01 plus 2000, which is equals to 2100 watts. This is my PO. Okay, this is my PO. So let's cross verify, right? Let's write PO equals to VO average into IO average. What is VO average? VO average is basically this, right? 21. IO average is how much? IO average is 100 into 100, which is exactly equal to this 2100 watts. So you can see, right, both are the same thing. Only valid I will write here itself, because many students do this wrong. They just remember this formula, and when in the actual examination current is not constant, they get it wrong. So only valid when current is constant. Okay, so like we check this. Now let's go to the next question. This is like just like a theoretical question here, right? Which of the following statements is /r correct for the given, like for the circuit shown in the figure? Load current can be continuous for any value of alpha. Load current can be continuous for any value of alpha. Here, it is true. Load current can be continuous for any value of alpha. Is it true? Given ratio of load inductance to resistance is very high. So if my L by R is very high, right, then it will take more time to discharge, and as it take more time to discharge, then load current will be continuous always. Load current will be continuous because this inductor will keep this freewheeling diode on until this SCR is triggered. So this first statement is correct. Load current can be constant for alpha less than 120 degrees. Load current can be constant for alpha less than 120 degrees. Given ratio of load inductance to resistance is very high. Again, this is true. Load current can be constant for alpha greater than 120 degrees as well, given it like this is very high, right? This L by R is very high and it discharges at a very slow rate. So this is again true. Okay, so there will be minimal repel. Load current can be discontinuous if the ratio of load inductance to resistance is very low, which is correct. Right? If the ratio of L by R is very low, then obviously if my L by R is very low compared to the time period, then obviously it will discharge very fast in the negative half cycle, very fast in negative half cycle. Okay, so obviously it will discharge in a very fast manner, and obviously like that load current will be discontinuous. There won't be continuous conduction. Load current will always be discontinuous, no, right? It won't always be discontinuous. It depends on the value of L by R. It depends on the ratio. Okay, so A, B, C will be my answer. A, ABC. Okay, next, calculate converter efficiency and supply power factor for the circuit shown in figure if load current is considered constant. Okay, so calculate converter efficiency and supply power factor for the circuit shown in figure if load current is considered constant. Yeah, so load current is constant, right? If the load current is constant, we have to find out the converter efficiency and supply power factor. So like what is converter efficiency? Converter efficiency, right? Converter efficiency is what? It is PDC upon PO. This is my converter efficiency. So like here they haven't mentioned for battery specifically. So I will directly write this. PDC is equals to what? PDC is equals to IO average whole square into R plus E into IO average divided by IO RMS whole square into R plus E into IO average. Now if the load current is constant, right? If the load current is considered constant, so obviously IO average will be equals to IO RMS. IO average will be equals to IO RMS. Hence this will be equals to 1. Okay, hence this will be equals to 1. So next what is the case? Next I can say that power factor, right? Supply power factor. So what is the formula for supply power factor? Cos phi s, right? Cos phi s is equals to PS upon SS. So PS is equals to PO basically. PS is equals to PO basically, and as load current is constant, right? I can directly say this is VRMS VS RMS into IS RMS, and this will be what? Simply I can say this as PODC, right? Because DC power will be same only, but I can still write this as it is, that is IO RMS whole square into R plus E into IO average. Now what is VS RMS? VS RMS is VM by root 2. This won't change anyhow. And what is IO RMS? IO RMS they haven't told us, but we can definitely compute it, right? We can compute the VO average, and from there we will be able to compute the IO average, and IO average will be equals to my IO RMS, because here load current is constant. So what I can do is I can compute just I'm checking if there is some lip syncing issue. I think there is a bit of lip syncing issue with the recording of this. I don't know. So here I can say my VO average will be what? You can remember the formula or you can derive. It will take you 10 seconds to derive. Vm by 2 pi into 1 plus cos alpha. So alpha they have given, right? Alpha is 60 in our case, and Vm is 230 root 2. Pi 1 plus 1 by 2 230 into 2 divided by 2 into pi into 1.5. 77.65 volts. Okay, so this is my VO average. Okay, this is my VO average. What about my IO average? IO average will be simply my VO average minus E by R. Okay, so here what can I say is VO average is what? VO average I've just computed 77.65 minus E is 30, R is how much? R is 10, I think. R is 10, so it will be minus 30. Okay, no, I did something wrong. No, okay, 77.65 minus 30 divided by 10, it will be 4.7, right? 4.765 amperes. So it will be 4.765 amperes. I will just quickly compute. 4.765 amperes. Okay, so this will be my IO average. And like, what will be my power consumed? Power consumed, right? PO will be IO RMS whole square into R, or you can do it otherwise also, VO like VO average into IO average, like that also you can do. Okay, so like this will be basically 77.645 into 4.765 divided by this SS, right? This is VM by root 2. So this is 230 into root 2. Oh, this is only 230 only into what? IS RMS. Now what is IS RMS? So here, right, until when my device conducts. So this device SCR will conduct from, SCR conducts from what? SCR is triggered at omega t equals to 60 and it will be on till 180. Why? Because after pi, supply becomes negative and hence SCR will be naturally commutated, and what will happen is that this will be turned on, right? This will be turned on. So this freewheeling now will be on. So it turns on only for 120 degrees. So for this case, right, how the current looks? The current, right, I can say here, the current will be on till only this time, right? It is off here. Okay, then it is on, then off, okay. So obviously this will be something like this. So like, what will be the IO RMS? What will be IO RMS? So IO average equals to IO RMS. What will be IS RMS? My IS RMS, right? IS RMS will be simply IO into 1 by 3 under root. Why? Because like that's how the formula is derived. You can like see my complex power lecture there. I have explained how does this 1 by 3 come up. Okay, so this will be 1 by 3 because like for a overall period of 2 pi, this is only conducting for pi by 3, for pi by 3, right? No, sorry, for 2 pi by 3. Okay, so this is only conducting for 2 pi by 3. Okay, so that's why this will be 120 upon 360 overall 1 by root 3. So this will be 4.765 into 1 by under root 3. So 77.645 into 4.4. Okay, 4.75 gets cancelled, divided by, okay, 77.645 divided by 230 and into 300. Okay, so 0.0922 0.5922 5. Okay, so okay, this is not PO actually, sorry, this is cos. I was writing PO, but I directly solve for cos phi s, so this will be cos phi s. Okay, this will be cos phi s, and this will be lagging. Why this will be lagging? If you compute the Fourier series coefficients, right, all the current components will lag. Okay, all the sinusoids will lag. So this will be your answer to the question. Let's come to the second question. Just hold on a second. I will check one thing. Yeah, let's come to the second, this 22nd question, right? So here, like a single phase half wave uncontrolled rectifier is given with transformer. Why do we use transformer? Basically to output, isolate the input and output. Why do we isolate? Because if some fault happens in the supply end, that shouldn't affect my load end. Okay, and if some fault happens in the load end, that shouldn't affect my supply end. This is used in our the grid transmission lines, right? Grid power systems. So this we will learn in the power systems subject. Okay, don't worry about that. But here two diodes D1 and D2 are given, and also they have told us this is used for isolation. Assuming the load current to be constant, load current is constant, and voltage is what? Vm sin omega t. V is Vm sin omega t. The current waveform through the diode D2 will be. So this is a freewheeling diode, and they are asking you the current waveform through this. And this is, just remember, right? This is a normal diode, right? Not a SCR, not a silicon controlled rectifier. This is just a normal diode which we cannot control. So obviously, once I get some positive voltage, right, what will happen? This will charge. This inductor will energize. Then as soon as the voltage become negative, so the voltage across this diode comes negative, because this cannot block any voltage, this cannot block any forward voltage. So as soon as the voltage becomes negative, right, what happens is this will turn off, and what will happen? The inductor will de-energize through this diode D2. So at omega t equals to pi, this will de-energize at diode D2. And what will the current? As they have told us, the current is constant. So obviously the de-energizing current will also be constant. The energizing current will also be constant. Okay, as like assumption is L by R is very, very large, because they have told us current is constant. So obviously from pi to 2 pi, what will happen is the current will be constant. So current will be constant. It will be from pi to 2 pi. Okay. So this won't be like exponential like thing, and this won't be conducting from 0 to pi. It will only conduct from pi to 2 pi. This is also wrong, right? Because this is not a SCR, this is simply a diode. So diode will conduct from pi to 2 pi, and this will not be exponential. This will be just constant current. So option D will be correct. Okay, option D will be correct. So that will be the correct answer to this question. Now let's come back to the next question. I think I've taken this question in chapter 1, I think, or I don't remember. The circuit shows an ideal diode connected to a pure inductor. Okay, connected to a pure inductor and is connected to a purely sinusoidal 50 Hz voltage source. So this voltage source is purely sinusoidal. Under ideal conditions, the current waveform through the inductor will look like. Under ideal conditions, what will be the current waveform look like? So obviously what will look like? This is a simple diode, right? And we have analyzed this very well. So from 0 to pi, this diode will be on, and this inductor will energize. So VL will be positive and IL will always increase, right? So from 0 to pi, this is half cycle. Half cycle is what? For a 50 Hz supply, half cycle is basically 10 milliseconds in time domain. Okay, it is pi in radians, and it is 10 milliseconds in time domain. So here 10 milliseconds, and current will only increase up until 0 to 10. From after 10, right? After 10, what will happen? Current will only decrease. Current will only decrease from 10 to 20. 10 to 20. Okay. So it will only decrease. So it will start from 0, it will end to 0. So 10 to 20, it will reach maximum at 10, and it will go to 0 at 20. Okay. Go to 0 at 20. So that is the case. So this is how we will this is how the waveform will look, not like this, right? This will not go to 0 at 10 milliseconds. Current will not go to 0 at 10 milliseconds. Current will only increase. Here it is telling that current will reduce before 10 milliseconds. Not possible. Here also not possible. Here also not possible, right? All these are cancelled anyways. So only option C is the correct one, because current will increase till 10 milliseconds and then it will decrease till 20 milliseconds. So this is simple only. Okay. So nothing much to worry. Just you have to find out the half cycle time period. So current, I will say, current will increase from 0 to pi. So what is pi? Pi, like I know, right? 2 pi is what? 2 pi is 1 by 50. Then pi will be simply 1 by 100, which is 10 milliseconds, right? And one more thing I can say, that current will current will decrease from pi to 2 pi. So like waveform will be something like increase and then decrease. So option C will be the correct answer for this question. Let's come to the next one. A single phase 1 pulse converter with an RLE load has the following parameters. A single phase 1 phase converter with an RLE load has the following parameters. Supply voltage is 230 volts. Frequency is 50 hertz. Load resistance is 30 ohms. Battery, right? The battery voltage is 110 ohms. The extinction angle is given. Firing angle is given. What is the voltage across the SCR when the current decays to 0? Okay. So when does the current decays to 0 for a RLE load? Okay. It decays to 0 at omega t equals to beta, right? At omega t equals to beta, it decays to 0. RLE load has the following parameters. So also they haven't told us that it has a freewheeling diode, so I will assume it doesn't have any freewheeling diode. If it had a freewheeling diode, they will mention it. Okay, so at omega t equals to beta, I have to tell the voltage across the SCR. So what is the equation for a voltage across the SCR? So as soon like current goes to 0, right? And then the change in current is also 0. So voltage across the inductor will also be 0. And as the current is 0, the voltage across the resistor will also be 0. So voltage at the cathode side will be simply E, and voltage at the anode side is always Vs. So it will be Vs minus E equals to Vm sine beta minus E, right? I should also tell here, because like I haven't mentioned what is the polarity of the voltage. I should write here what is the anode to cathode voltage across SCR. Then this will be much better terminology, because obviously the polarity is also important, right? Polarity is also important. So here, right, Vm sine beta minus E, Vm is 230, so this is 230 root 2 sine beta is sine 235 minus E is 110 volt. So I will just compute this. What will be this value? 230 into 2 into 235 sine minus 110 volts. So it is minus 376.45, almost minus 376.45 volts. Okay. Let's go to the next question. So in the next question, this is also a gate 2014 question. So here the circuit shows a circuit diagram of a rectifier with a freewheeling diode. The load consists of a resistor and an inductance, okay, of 0.05 Henry connected in series. Assuming the ideal thyristor and ideal diode, the thyristor firing angle needed to obtain an average voltage of 70 volts. So this is mainly just like a formula based question only, because like for a diode, right, with this voltage, with freewheeling diode, for a rectifier with freewheeling diode, the average voltage formula we know, but that is only valid for continuous conduction. So is the conduction continuous? So most cases the conduction will be continuous, but if you want to check, you can check, right? Conduction will be continuous. L by R is what? This 0.05 Henry is actually very large, divided by R is 10, right? And this equals to this is in milliseconds. So this will be, if I multiply this by 1000, 5 by 100, so this will be 5 milliseconds. Okay, and what is 4 tau? What is 4 tau? 4 tau is 20 milliseconds. Okay, and here, right, what is my T by 2? T by 2, right? T by 2 is, this is my tau, 4 tau actually, and my T by 2 is 10 milliseconds. So obviously my discharging time, I have more time to discharge, right? It will discharge in 4 time and it has t by 2 time to discharge. So obviously my discharging time, my time to discharge is very high than the time for which it will be able to discharge. So obviously it will not discharge fully. The load current will be continuous. So from this I can deduce that load current will be continuous. And if the load current is continuous, right? And if the load current is continuous, load current is continuous. So if the load current is continuous, what can I say? My VO average will be simply Vm by 2 pi into 1 plus cos alpha. VO average will be Vm by 2 pi into 1 plus cos alpha. So this will be equals to what? So they have told me, right? Specifically they have told me I need a VO average of 70. Then what should be the firing angle? So I need this equals to 70. So Vm is also, they have told me, it is 325. 325 divided by 2 pi into 1 plus cos alpha is equals to 70. I will just quickly compute this. So all these are mainly formula based question, or numerically based question. So not that brain you need to use. So divide by 2, divide by pi into 70, subtract by 1, then cos inverse this. So alpha will be 69.31. Alpha will be 69.31. Now you need to be careful which units they have asked in. The thyristor firing angle in degrees. So be very careful here, right? Be very careful here. If they would have asked here in radians, then things would have changed here, right? So you have to be careful. Now your answer will be 69.31. That will be your answer. Okay. Next question. A single phase 1 pulse converter. A single phase 1 pulse converter supplies a resistive load with the following specification. A single phase 1 pulse converter supplies a resistive load with the following specification. Source voltage is 230 volts at 50 Hz. So this is in RMS, right? Remember, this is in RMS. I will write here. Okay. E is 100 volts and R is 100 ohms. Okay. If the thyristor is continuously triggered by a constant DC, what is the peak inverse voltage across the thyristor? So they are asking us the peak inverse voltage if the thyristor is continuously triggered by a constant DC. Okay, that means what? Always on. Not always on, sorry. Basically alpha is equals to alpha minimum. Okay, because it is acting like a diode. Because whenever this is in the forward blocking mode, it is instantly turning into the forward conduction mode because the gate trigger circuit is always on. So this is basically acting like a diode. Okay, this is basically acting like an uncontrolled rectifier. So I have a single phase 1 pulse converter. Okay, it supplies the resistive load. So I have a resistive load and ER load, right? And obviously I don't have a any emitter here. So what will the peak inverse voltage across the thyristor? Very simple, right? Very simple. So if my thyristor is something like this, this is like just like a diode. This is my Vs and this is my this is my E, right? E voltage. And at, like during reverse bias, this will be off. Okay. So my Vt, right? Vt will be simply Vs minus E, and during in the reverse bias condition, Vs is negative, right? So maximum value of the voltage in reverse bias condition. Okay. Maximum negative value of voltage across the diode. So that is, this is what? Minus Vm minus E. What is Vm? Vm is 325 because this is the RMS value, right? This is the RMS value. So it will be minus 325 minus 100, that is minus 425. And they are asking us the peak inverse voltage. Peak inverse voltage is basically the magnitude of the reverse voltage, right? Magnitude of the reverse voltage across the diode. So PIV will be equals to 425 volts because this is just not a thyristor. This is just a simple diode, right? Nothing to scare here. And basically alpha minimum in for a RE load is what? It is theta, right? It is not 0, it is theta. Okay, because before theta the SCR is off, like in the reverse blocking mode, right? In the reverse blocking mode. Now obviously all the questions are done. Like this was, last one was easy only. Now we'll solve the single phase half rectifier with capacitive load. Here also there is a very good concept. Just learn this, okay, because if your transient is very good, right, you will be able to blaze through this. So here I have a pure capacitive load and Vs is this. So here what I can say is that let's analyze this with a uncontrolled, that is with a diode, okay, for now, and then we'll analyze this with a SCR as well, okay. So for now we'll analyze this with a simple diode. So this is uncontrolled. Okay, so here what is happening at t equals to 0 plus. So we will again understand if omega t is greater than 0, if my diode is initially, I will assume my diode is initially off, then what is happening? So obviously there is no initial charge across the capacitor, so I will assume that my Vc0 minus is 0 only, and I know that capacitor doesn't change its voltage instantaneously. So as soon as this voltage is applied, right, so what is my Vd? Vd is simply Vs minus Vc. So Vc0 minus is 0, right? So it is simply equals to Vs Vd. So it is simply greater than 0, right? If it is greater than 0, that means my diode is forward bias, hence diode will be on. Now as diode is on, what is happening? A sinusoidal source is directly connected across the diode. Okay, a sinusoidal source is directly connected across the diode. So it will be a sinusoid response basically. So, and another thing is that if I assume my diode to be on, then my VO becomes what? VO is equals to VC equals to Vs. And what do I know? That my Vc0 plus is what? Like a sinusoid waveform just at omega t equals to 0 plus. What is it? It is just very near to 0. Very near to 0. Just increasing a bit. So here I can say almost equals to 0 volts only. Okay. Almost equals to 0 volts. So I can say that Vc0 plus equals to Vc0 minus, because previously as well the capacitor had no charge. So it had no voltage. So I can say that no impulse current will flow. Okay, so that we can say. Okay, so no impulse current will flow because Vc0 minus is almost equal to Vc0 plus. And what is my Vc? Vc equals to Vc of t equals to Vm sine omega t, right? Vc equals to Vm sine omega t. So can you tell me what will be my IC? IC will be simply what? The differentiation of this, right? So IC of t will be C dVc by dt. So it is C dVc by dt. So here what I can say is this is C omega, because it is omega t, so omega is a constant, omega Vm cos omega t. So I don't have space, so I will write this in the next slide. Okay, I will write this in the next slide. Take the next slide. Okay. C omega Vm cos omega t, right? Cos omega t. So what I can say is that after this, right, when let's say when my supply voltage reaches this Vm, when my supply voltage reaches Vm. So here, if I just compute one thing, as soon as my supply voltage reaches Vm, and just after that, just at omega t equals to pi plus, what will happen is that capacitor will not allow change in voltage. So it will try to keep it voltage at Vm, because like this output voltage of the capacitor is just following the input voltage, right? So it will try to keep it voltage. This node will try to keep it voltage at Vm, and this node is telling what? This node is telling that I am reducing my voltage at this node. I am some lower value than Vm. So the anode to cathode voltage Vd, right? VD will go below 0. Once it goes below 0, things become very simple. So diode turns off and diode turns off. Now can you tell me when will the diode next time turn on? Diode on. When will the diode next time turn on? When it will turn on? It will never turn on. Why? Because this value, this node, right, is fixed to Vm. Can this node ever go up Vm? No, right? The maximum potential that this supply can provide is Vm. It can never go above Vm. So this diode will never be on. Because for this to be on, the anode to cathode voltage needs to be positive. Basically, the cathode voltage is fixed to Vm. So this needs to be greater than Vm, which is never possible because this supply can only provide Vm voltage. This supply can only provide Vm voltage. Okay. So that is the case. That is the case. Now what I can say is that at pi by 2, right? So no, sorry, not at pi, sorry, at pi by 2. This is at pi, right? This is at pi. So at pi by 2, this has supplies Vm and then capacitor remains at Vm. Capacitor voltage remains at Vm and it stays like that. Okay. And what is with high voltage? So this voltage, right? This will be always 0 because diode is on here. Okay, not always 0. Diode is on here. Then, right? Then what happens is that this VD voltage will be simply VD will be. I will just write the expression here. VD will be simply Vs minus Vm because this will be stuck to Vm, right? This will be charged to Vm. So I will shift this whole thing below by Vm. So this thing, right, this will be here, and just if I can copy this, can I copy? I cannot. This will be shifted by Vm. This will be like this and this will be so up until here, right, the diode voltage will be 0 because it has turned on. It has turned on. This is after omega t greater than pi by 2 because after pi by 2 diode never turns on. Okay, this is the case. So like these are the waveforms of this is not t actually, this is t, right? Vd. Okay, so this is the case. Now let's understand this. This is not pure inductive, this is pure capacitive. With the SCR, right? What will happen with the SCR? So my voltage is Vm sin omega t, the input voltage, and let's say I am not triggering it right now. I'm triggering it at alpha. But first of all, let's understand the forward blocking mode for this. So here again, if my initial Vc 0 minus is 0 volts, so what I can say? I can say it like this, that the voltage, right, voltage across the thyristor, voltage across this thyristor will be something like this. Just it will be the supply voltage because the cathode voltage is 0. So my what I can say? I can say that my Vt will be equals to Vs. Vt will be equals to Vs, that is Vm sin omega t. If whenever my thyristor is off. So again, what I can say is that this is my like control region. Okay, this is the region in which I can control. And this is the region in which I cannot control, uncontrollable, right? Okay, so now what I can say is that at alpha this will be triggered and things will happen. That will understand. Okay, so but my range of alpha is what? Range of alpha is from 0 to pi for now. Okay, because as soon as the SCR gets turned on, things will change. So we'll understand what will happen. So case 1 is pretty simple. From 0 to alpha, this is off and nothing is happening. Okay, basically my IS is equals to my IT is equals to my IO is equals to 0 amperes. Okay, and my VO is equals to VL, not VL, sorry, VC of 0 plus VC of 0 minus, that is 0 volts only, because capacitor voltage will remain at that, and my VT is equals to VS, and as VS is positive, hence like it is proved that my SCR will be in forward blocking mode. Okay, SCR will be in forward blocking mode. Next is case 2, from alpha to question mark. So we don't know what this question mark is. We'll understand this. So at omega t equals to alpha, SCR is triggered. SCR is triggered, right? So SCR is triggered. Then if SCR is triggered, my thyristor voltage will be 0, and what will happen? My V output voltage, right? Output voltage equals to my capacitor voltage equals to my Vs, which is greater than 0. Okay, but VC like before that, right? Before, what was VC? Alpha minus, it was alpha by omega, actually alpha by omega minus, it was 0 volts. But VC alpha by omega plus, it is telling that it is some non-zero voltage, right? It is fixed to some voltage that is equals to my Vs, okay, which is greater than 0. So what will happen? It is not matching. Voltages are not matching. So here there will be 3 cases here that we will understand. First case is if my alpha is lying between 0 to pi by 2. So if my alpha is lying between 0 to pi by 2, what will happen is that my Vs can lie between what? Vs can lie between plus Vm to 0. Okay. So my VC0 minus is 0 volts. VC0 minus is 0 volts. And my VC0 plus is what? My VC0 plus is Vs, which is a mismatch. So obviously impulse will flow. My VC0 minus is not equals to my VC0 plus. So what will happen? Impulse will flow. Okay, a impulse will flow. Now if an impulse flows, what will be that what will be that value? So as soon as the impulse flows, then my VC0 plus becomes fixed to this Vs, and then I can simply compute the current, right? Then my VC settles to Vs, and then my IC will be the same expression as the previous case. Just here, right? What happened is that impulse thing was extra, because VC0 plus was not equal to VC0 minus. So now it will be same. ICT will be equal to C dVc by dt. So this is equals to CVM cos omega t. Okay, so this will be the ICT. Now if what happens is, if for some reason this is not the case, if it is triggered from alpha to omega t, and after what now it is triggered here, right? Like if my alpha is between 0 to pi by 2, so what will happen here is that in this case is itself, if my alpha is between 0 to pi by 2, what will happen is, this is not case 2, actually this is the case 2a only. Okay, case 2a only, we're continuing with the case 2a. Okay, now okay, I should write here one thing. Case 2a. So from alpha to infinity, right? Alpha to infinity, what will happen is that anything am I doing wrong? No, not from alpha to infinity. This should be from pi by 2 to infinity. Okay, this should be from pi by 2 to infinity, not alpha to infinity. Sorry, pi by 2. So at pi by 2, what will happen? At pi by 2, my SCR at omega t equals to pi by 2, my SCR will be naturally commutated. Okay, naturally commutated. Now why is it naturally commutated? Same reason as the previous case, right? Diode case. So as soon as this node reaches VM, this node doesn't want to go below VM, right? As soon as my node reaches VM, this node doesn't want to go below VM. This is fixed to VM and this node goes below VM, right? This node goes below VM, hence what happens? The thyristor goes into reverse blocking mode, right? Thyristor goes into reverse blocking mode and that's it, right? That's it. So the waveform will be almost like the previous case. Just here, what will the difference is that there will be impulse current. There will be impulse current and then the waveform will be something like this, right? Like the current will be reducing and here the current will be 0 and that's it, right? Basically, as soon as the current becomes 0, the SCR is naturally commutated and it is 0 forever because this node voltage can never go above VM. This will always be below or equals to VM, right? So that's why the thyristor is always in the reverse blocking mode. Let's go to the next case. Next case is 2B. So here, right, I am taking the case for if my alpha is between pi by 2 to pi. If my alpha is between pi by 2 to pi, what will happen? Like I can name this case as pi by 2 to 3 pi as well, because okay, pi by 2 to after pi, right? After pi, it will never turn on because this is 0 and this is anyways negative, so this can never turn on. Okay, so if my alpha is between pi by 2 to pi, what will happen? If my alpha is between pi by 2 to pi, this like SCR will turn on. Okay, as this is 0 and still this is some positive value in this region as well. My VS is going from what? This time, right? My VS is going from a VM to, the important thing to note here is VM to 0. Okay, so VS is reducing. So as soon as this turns on, right? As soon as this turns on, so my VC of alpha by omega plus will be equals to VM sine alpha. And after that, what will happen is that the voltage VC will get fixed to this and my VS will reduce. If VS reduces, then this node voltage reduces, right? This node voltage reduces and this node voltage is what? This node voltage is VS sine alpha. This node voltage is VS sine alpha and this node voltage is fixed. VS sine alpha fixed, right? This is fixed. Okay, so this is fixed and this is reducing, so obviously instantly it will turn off. So here, right, what will happen is that a impulse current will again flow and it will instantly charge as my VC of alpha minus by omega is not equals to VC by alpha plus by omega. Hence what will happen? A impulse current will flow. Okay, a impulse current will flow and it will instantly charge and then the SCR will be instantly turned off after that because this node is reducing only. So between this alpha to 3 pi minus alpha means what? This means basically at the starting of this sinusoid. So if I draw the sinusoid, like here, I think I have drawn, okay, I haven't drawn it here. Okay, I will draw it here again. So this right, this is B, this should be also B, okay, because this is for the part B1, so this will be for the B part. So here this omega t, this is Vs, okay, so this will be what? This will be basically my waveform. So my sinusoid waveform, right? Let's say this point at this alpha, it was triggered. At this alpha, this was triggered. Then after 2 pi, again I will get back to this value, but the difference will be here, right? This will be like this is alpha. So if I add 2 pi with it, so this will be 2 pi plus alpha, right? 2 pi plus alpha. But I'm not triggering my device here. I'm not triggering my device. My device is getting triggered at what? Like this is sinusoid, and then again it will come back here, right? Again it will come back here. Okay, sorry, this is not actually 2 pi plus alpha. Sorry, this is actually, this will be what? I'm sorry, this is if this is alpha, right? This is alpha, then this will be what? This will be alpha minus, sorry, pi minus alpha. This will be pi minus alpha, and if I add 2 pi with this, this will be 3 pi minus alpha. Okay, this will be 3 pi minus alpha. Yes, correct. So here, right, here what will happen is that this is 3 pi minus alpha. Exactly, I am talking about this value only. This voltage, this node voltage will again come back to Vm sin alpha. Okay, hence what will happen, my SCR, right, was in reverse blocking mode here. It went to reverse blocking mode because the voltage across it became negative. But here, this SCR will be in forward blocking mode again. SCR will be in forward blocking mode again. Okay, so it will be again open only, no current will flow. Then sorry, yeah, I'm talking about 3 pi minus alpha. From alpha to 3 pi minus alpha only, this will never turn on. Because why? Because this voltage is reducing, and this voltage is fixed. Okay, hence this will again, like the anode to cathode voltage will be negative, hence this will be off only. Okay, so this is the case. And 3 pi minus alpha, 2 pi plus alpha. So okay, now from 3 pi minus alpha, sorry, I will, like this SCR is in forward blocking mode in this region, and SCR is in reverse blocking mode in this region, right? SCR is in reverse blocking mode in this region. Okay, and SCR is in forward blocking mode here. Okay, so SCR will be still off here. Then after this, right, after 2 pi plus alpha, this, like up until 2 pi plus alpha, this is 2 pi plus alpha because I will add 2 pi with it, and this point, right, this point will be 2 pi plus alpha when I will reach back to that angle where I will trigger my SCR, right? After every 2 pi I will trigger my SCR. Okay, so at 2 pi plus alpha I will trigger my SCR, and will it turn on? No, right, it will not turn on, because here this node voltage is same, this node voltage is same. It will just remain at the same state, and then again at that instant the voltage will reduce, again it will go to reverse blocking mode. So this voltage will, this capacitor voltage, right, it will always remain at Vm sin alpha. This capacitor voltage will always remain at Vm sin alpha. Okay, and if obviously my alpha is greater than pi, it will never turn on. Vc will be always 0. Another fourth case will be like, not fourth case actually, I will just write here. Case 2c. Case 2c. If my alpha is between pi to 2 pi, SCR never turns on. SCR never turns on. Why? Because it is always in reverse blocking mode. It is always in reverse blocking mode, right? It is never in forward conduction mode. It is always in reverse blocking mode. Okay, so SCR will never turn on, and output voltage will be 0 always. But in this case, what will happen? In this alpha angle, it will trigger once, and it will remain at Vm sin alpha because the impulse current will flow. It instantaneously charge this. The value of the sin current will, like the value of the impulse current will be Vm sin alpha delta of t. Yeah, because also a C will be there at C dVc by dt. So a C also will be there. Okay, C times this. Okay, C Vm sin alpha into delta of t, that is the area of this impulse, and then it will remain at that, because after this point, right, I will trigger my SCR here only, and if I trigger my SCR here, the anode to cathode voltage is 0, and just after that it goes to negative. Hence this here will not turn on, and this will remain at this. This will remain at this. Okay, so this will be the waveforms of capacitor. So this is very interesting analysis, and many people don't cover this. I'm pretty sure one day GATE will again ask a question from this, and many people will not be able to solve this. Now, what are the advantages of a capacitive filter? So basically, right, I told about inductive filter. What are the advantages of capacitive filter? I've explained this in my prerequisites as well. It reduces the ripple in the output voltage because it tries to maintain the output voltage, right? Tries to maintain the output voltage, and then average value of the output voltage increases because here, right, you can see, right, it tries to fix the output voltage to some value. It will help it increase the output voltage, and as the average output voltage increase, the efficiency will also increase. They are interlinked with each other. Okay, so like here we have one very simple question with capacitor. Okay, so here you have to compute the average power dissipated by the load resistance R for the circuit shown below. So what will be the power dissipated by the load resistance R? Okay, so how do you compute that? So basically, right, here what happens at t equals to 0 plus, this diode will like this diode will turn on because this end voltage is 0 volts, Vc0 minus is 0, and this is some positive value, very small. So that will turn on, and it will what? It will, like, the capacitor voltage will follow the input voltage. Now as soon as it gets to Vm, what will happen? This voltage is reducing, and this is equals to Vm. This node is trying to stay at Vm. So this diode will turn off. As this diode turns off, what will happen? This capacitor will discharge through this. This capacitor will discharge through this resistor, right? There is a resistor as well. I have to understand what is the time constant of this circuit. If the time constant is very, very high, that means it will take very high amount of time to discharge fully. Okay, so it can't discharge fully. So then what will happen is that this, right, this node will almost always remain at Vm, almost equals to Vm only. So I will compute my time constant. So this is the key, this is the one that I analyzed in the first case, right? First case, just a resistor is present over here. A resistor is present over here. What is my time constant? Time constant is R into C. Time constant of the discharging circuit, not the charging, right? When it is charging, I'm talking about discharging. If you have studied transient very well, you will understand all these things. So during discharging, right, this part is only active, this part is not in the action. So this part, right, here C and R in parallel. Okay, so it is RC. What is RC? RC is 1 second, right? 1000 milliseconds, that is 1 second. And what is my time period? Time period is only 20 milliseconds, right? Time period is 20 milliseconds. So I can safely say my 4 tau is very, very, very large than T. So how will my output voltage look like? So for the first transit, right, from 0 to pi by 2, omega t equals 0 to pi by 2, this will be Vm. Okay, then what will happen? It will discharge, but very slowly, very slowly. Then again, what will happen? At some point here, right, the anode voltage will be just higher than the cathode voltage. Then again, it will charge very fast. Okay, charge very fast, because charging, right, during charging, the voltage, input voltage is directly connected across the capacitor, so it will charge instantaneously. So then again this will reach to some Vm value, then again it will discharge very slowly, and this will follow. Okay, not like this. Here I am zooming it in and showing you that yes, it is discharging, but in actual case this will discharge very small amount. But to show you, right, I have to show this thing that it is, yes, it is discharging, but very small amount. It is discharging by very small amount. So it will be almost, my output voltage, right, my VO will be almost equals to Vm. Okay, I can assume that my output voltage will be almost equals to Vm. So if my output voltage is almost equals to Vm, so this voltage, right, is fixed. This voltage is fixed. That is constant. So what is my power dissipated across the resistor? It will be like, the voltage is fixed, right? It is Vrms whole square by R. And as the voltage is fixed, that means Vrms is equals to Vm. So what is Vrms? Vrms is 230 root 2 whole square divided by R. What is R? R is basically 10 ohms, right? R is basically 10 ohms. So what will be this equals to? Where is my calculator? Yeah, calculator is here. Just hold on. It will be 230 into 2 under root whole square divided by 10. 10580. Okay, 10580 watts. Okay, so like this will be the answer to this question. Let's go to the next question. So next question is basically this: the block diagram of AC to DC 1 pulse converter with freewheeling diode is shown in the figure below. So the block diagram of an So off, I have missed every time. Of an AC to DC 1 pulse converter is with freewheeling diode is shown in the figure below. The type of load for the output voltage waveform as shown. So block diagram is shown and the output voltage waveform is also shown, right? So here this is some constant value. That means E load must be present here, and this can't be only AC load because this is some constant value here, like the it is not conducting. It is not conducting. It is like here what has happened, the load current is getting 0 here, and then again the voltage is some constant value. Okay, here I have done this wrong. This should be actually, this should be some positive value, right? This should not be some negative value, this should be some positive value. Yeah, that is my wrong for me. Okay, so if the load was inductive, right, if the load was only inductive, it would have always followed the input, right? It would have kept the cell on, it would have always followed the input, but that's not the case, right? And if it is capacitive, it would have charged to some value, it would have remained that. So DC motor is the correct one. Why DC motor is the correct one? Because simply what is happening, DC motor is what? DC motor is RLE load, right? RLE load. And in case of RLE load, due to the inductor, it keeps it on for a certain amount of time, then it extinguishes, right? Then the current extinguishes. So this value, right? This value will be beta, and then the current extinguishes, and that's it. The device turns off. And the voltage is E. So like it is a RLE type load, and DC motor is a RLE type. If you have studied electrical machines, you will understand that there is a resistor, inductor, and a battery, obviously that is known as back EMF. Okay, so that's it basically for half wave rectifier. We are totally done with half wave rectifier, even though they don't ask too many questions from half wave rectifier. But if your basics are clear here, right, we will blaze through the full wave rectifier. We will be able to easily understand all the concepts because your fundamentals need to be clear for analyzing a particular circuit, right? So I've tried to clear all the fundamental things. I've tried to tell you that which formula you can remember, which formula you can derive within seconds as well, and which formula you don't need to remember. So that is also important, right? Which you need to skip because you have limited amount of time. You have only 1 year to 2 year time of preparation, and you have to understand which part you need to study and which part you need to skip because your main priority is getting a good rank, and then doing M.tech in some IITs or ISC, okay, or some top university. But the most important part is we don't just tell you to mug up the formulas, we tell you the concepts as well. That is the most important part. So thank you for watching, and I will see you in the next lecture with full wave rectifiers.